This video is about limits of complex numbers, and we're going to break it down into two subcategories, sequences and functions. So first we'll talk about sequences. A sequence, two of which I've written here, is just a list of numbers. So the top one, 1, 2, 3, 4, 5, 6, so on, is a sequence. But the thing about that sequence is that it won't converge to any number, which means as the list goes on, it's not getting closer and closer to any number. In contrast, the sequence at the bottom, 1, 1/2, 1/4, 1/8, and you keep dividing by 2, this will converge to 0, which means that as you go closer and closer, this is getting closer and closer to 0. So let's see in the complex plane how to determine if some complex number is a limit of a sequence. So here's an exact definition. If we have the complex plane and we suspect the limit of some random sequence we have is p, then we can check this if this condition holds. All but a finite number of points lie in any open disk centered at P. So it seems a little bit complicated, but here's what it means. So pretend that we have our sequence, and we start plotting the points. So the first point of the sequence is here, then here, then here, and it kind of curves around like this, and then they get really, really compact as we start approaching P, which is why we think that P might be the limit of this sequence. So how to check that is, let's do exactly what the definition says. Take any open disk centered at P, and since it says any, we have to consider all open disks, so as small as possible. So let's just draw a small open disk centered at P. Okay, so keep in mind you can make this even smaller if you want, but is it true that all but a finite number of points lie in that open disk? Well, we see that in the open disk, the points are getting really, really compact, so there's an infinite number of them right here. And the only ones that are not in the disk is this range right here, and that's a finite number of points. We can count them. We can just go 1, 2, 3, and then as soon as we get inside the disk, we stop counting. So this is true. Now, let's see a case where this is not true. Let's say we thought maybe the limit was here at M. Now, if we take an open disk here, it's true that this open disk does capture a few of the points that I've drawn, but it's not true that all but a finite number of points lie in that open disk, because there's an infinite number of points right here that do not lie in this disk. So M is not the limit of the sequence, and P is, because of this condition. So that's kind of a graphical notion. So now let's just work out some numerical examples to get a feel for how we calculate it. And in truth, how you calculate it is very similar to real numbers. You just have to treat I as just kind of any other number. So let's see this one. Z sub n, so that means that the nth term is given by 1/2 plus I over n. So as n goes to infinity, this I over n goes to 0, and the 1/2 plus 0 is 1/2. So this goes to 1/2. Now let's look at this one. It looks a little bit more complicated, but really it's not. So this negative 1/3 to the power of n, this is all real. There's nothing imaginary going on here. So if we take n goes to infinity, this 1/3, since its absolute value is less than 1, this will get smaller and smaller and smaller, just like this sequence right here is getting smaller and smaller and smaller right here. So this part will go to 0, and then 1/3n will go to 0. So 2 plus 0 is 2, and then we have to multiply by I. So this goes to 2i. So these two do converge, as we see, just by kind of observing it. Now let's look at this one. Z sub n equals I to the n. So what's the first term? I to the 1 is I. What's the second term? I squared minus 1. What's the third term? Negative 1 times I is negative I. What's the fourth term? That is 1. So, and then what's the fifth term? 1 times I is just I. And we see that this is just repeating. It's just this repeating sequence of numbers. So as we go to infinity, as n goes to infinity, we can't decide on any of these that's going to be the limit. So in this case, the limit won't exist, and it's not going to be convergent like these examples. So you just kind of have to remember this rule about I, where it just repeats itself in fourths sometimes. Now let's look at some of the properties of sequence limits. So I've written down here. Let's suppose a sequence Z sub n converges to x, sequence S sub n converges to y. So what does the sequence Z sub n times S sub n converge to? So this sequence is what you get when you multiply term by term. So first term times first term is the first term of the sequence. Fifth term of Z sub n times fifth term of S sub n is the fifth term of Z sub n, S sub n, like that. So this will converge to x, y. Now, Z sub n plus ws sub n, where w is just any complex number, this will converge to x plus wy. So it seems like very intuitive. Now, Z sub n divided by S sub n, this will converge to x over y if y does not equal 0. because if y equals 0, then we get a problem in the denominator, undefined. So that's about sequences, and we'll come back to that in later videos. Now I want to talk about function limits, which is more important to our purposes. So before we do that, we need to go over two small topics, modulus and conjugate. Modulus of a complex number, which is given by, you put the absolute value bars on either side of it, is the distance from the origin. So here's our complex plane with our real and imaginary. Let's draw 1 plus I. 1, 1. So here's 1 plus I. What's the distance of that from the origin? Well, we use Pythagorean theorem. This is 1, this is 1. So this is radical 2. So this is square root of 2. Now, what's the distance of just the number 2 from the origin? Well, it's here. It's easy. It's just 2. What's the distance of 2i from the origin? It's the same. It's just 2 because you're going vertical 2 or horizontal 2 for either of these. So this is just 2. So that's modulus, which will be important in a definition in just a second. And while we're talking about that, let's talk about conjugate, which you might have learned already. Conjugate of a complex number is just you take the imaginary part and you flip the sign. So conjugate of 3 plus I is 3 minus I. Conjugate of minus 2i is 2i, because this is purely imaginary, so you just flip the sign. And conjugate of 3 is just 3, because there is no imaginary part, so the real part remains unchanged when you do the conjugate. So keep that in mind. Now let's talk about function limits. So you might remember the epsilon delta definition from single variable calculus, and this is kind of similar. So, except we have to kind of deal in 2 dimensions now, because remember, we're dealing with sets as domains instead of just segments of the x-axis. So let's try to dissect this. So now we want to find the limit of some function we have. We'll call it f of z. We want to find the limit of f of z as z approaches z naught. And here's z naught. So now something interesting to note is that you have to make sure that this limit exists no matter which direction you approach from. So with single variable calculus, you approach from either the left or right, and that's all you really have to check. Here, there's infinite cases you have to check from. You need to check if the limit exists when you approach this way, this way, even more convoluted ways like this really. You have to see if it's going to approach the same limit. And we suspect that the limit will be L. So we're saying that as we get closer and closer to z0, as we plug these points into the function starts outputting things that are closer and closer to this limit L down here. And here's the test to check that. So it's just like the epsilon delta game we played with single variable calculus, but now we're using open disks. So we're asking ourselves, if we want to get, let's make a nicely sized open disk around L. So if we want to get this close to L, if we want, every time we input something into the function, we want to get inside this open disk, so this close to L. Then how close do we have to get to z0 or z0? Well, let's just say the answer is like this. So what this tells us is that anytime we plug something in this open disk centered at z0 into f of z, we're going to get something in this range of L. And then we have to ask ourselves again, well, what if we want to get closer to L? What if we want to get into this smaller open disk? Well, then we have to get a smaller open disk around z0. So it's just that kind of game. And if you can keep playing that game arbitrarily, if every time you pick a radius for the open disk at L, centered at L, you can also pick a radius for the open disk centered at z0, such that whenever you plug those points in, you'll get points only in the open disk centered at L, then L is definitively a limit. That's the limit as z approaches z0 of f of z, is in fact L. So if you try to wrap your mind around it, it might seem a little bit complicated at first, but it'll make more sense as you go. And it kind of reinforces this definition that you approach from any direction, because this disk is approachable from any possible direction. So the last topic we'll talk about before doing a quick example is continuity. Continuity is just the definition that, so a function is continuous at z0, z0 for example, if limit as z approaches z0 of f of z, if f of z0. And this should seem familiar from calculus as well. So the continuous condition is that the limit exists. So I should write that. Limit exists and the limit is f of z0. So we have to have that when you plug z0 into the function, you get L. So it can't be undefined or anything. So now let's just do a quick example where the limit does not exist, and we're going to see why, because it has to approach from every direction. So let's use orange for this. So here's our task. We want to find limit as z approaches 0, so the origin, of z over z bar. So it seems I have two bars here, so let me write it in this form. Z divided by z bar. And remember, z bar is conjugate of z. So this seems a little bit menacing at first, because how do we prove the limit exists? Because we have to approach it from infinite directions. Well, it turns out that if we can find two directions where the limit is different, we can say it does not exist, because a limit has to be the same from all directions. So let's set out trying to do that. So let's try to find the limit as we come from the right on the x-axis, the real axis, approaching 0. So how does z, the independent variable, look in this case? Well, in this case, if we're approaching on the real axis, the imaginary part is 0. So let's just say it's x, where x is real. So for example, x might be 100, then maybe it's 10, then maybe it's 1, until we get closer to 0. So let's try to find limit as x approaches 0 of x over x conjugate. And what is the conjugate of a real, purely real number? Well, it's just itself, because it has no imaginary part. So this is just limit as x approaches 0 of x over x. And x over x is 1. So this is limit as x approaches 0 of 1, which is 1. So we found that approaching from this direction, the limit is 1. So it better be 1 from any direction, because if it's not, then this limit does not exist. So now let's, in purple, we'll find the limit as we approach from this direction, where we only consider the imaginary part and the real part is 0. So we say limit as, and let's call this y. So, and let's call it yi, where y is an element of the real numbers. So as, so we're going to put yi over yi bar as y approaches 0, right? So then what are we going to need to do? What is yi bar? Since we have purely imaginary number, like we did here, where we had negative 2i conjugate is just 2i, we just flip the sign. So it's going to be limit as y approaches 0 of yi over minus yi. And we cancel out the yi, equals limit as y approaches 0 of minus 1. And that is just minus 1. So amazingly, we have arrived at this contradiction. If we approach from this direction, the limit is 1. But if we approach from this direction, so this direction limit is 1, this direction limit is minus 1. And that fact alone is enough to tell us that the limit does not exist. And then we are done. So that's the powerful thing about these limits. It might seem scary because there's so many ways to approach it, but at the same time, if you find two contradictory ways, then you're done with the problem. The limit does not exist. So this is just a little bit about limits. We'll come back to it when we talk more about sequences, when we're dealing with more heavy stuff. So until next time.